sit here. Now we are going to start with the lightning talks. Just one rule, 10 minutes. So, Thiago, you have 10 minutes.
Great. So thank you everybody for coming. I introduced myself earlier today, so I won't do it again. I wanted to talk about optimizations with the SIMD, single instruction, multiple data, mostly on x86 because, as you can tell, I work for Intel. So that's the one that interests me. They exist in other platforms too. So before that, what is SIMD, right? So this is, I just copy-pasted from the Intel manual. It's one of the things that if you work with assembly, if you work with low level, you want to download the Intel Software Developer Manual, especially volume 3, which is the instruction listing. It has a bunch of diagrams. Don't worry that you can't see it very well. But basically what it is showing is that if you run one operation, for example, vage add PD, that is vector horizontal add packed doubles, right? You have like very interesting instruction names like p unpack byte high byte to word. We have one that we like to call the pickle muckle duck. It is the parallel carry less multiply double quad to double quad. Some interesting names like that. But the diagrams are showing you what it does. So for example, the example there of the horizontal add, take two elements, right, next to each other, add them up, and put them in the vector in the position. So you're seeing what it does there. The vector move double duplicate, it just duplicates, as you can see. So let's take another example here. So what happens if I use this unpack one, right? So this is a little expanded, a little bigger. So as it's showing here on the example, it just takes the high parts of the registers, right, and interleaves them. It's an unpack because I'm taking from two sides. I could pack, which is the other way around. Now, what happens if the top register is all zeros? I get zero extension, basically. I get an interleaving of zeros, which is basically just taking a byte and zero extending it to words, which is exactly what you're going to find in Qt in this function here, which is from Latin 1. So QString from Latin 1 is basically running this instruction over and over again. There are a couple of more optimized versions, but it also does the low and the high. As you can see in the code example, unpack low, unpack high, save. That's it, right? So this code that you're seeing here expands to assembly that reads, I believe it reads 16 characters, 16 bytes, and writes 32 bytes, so 16 QChars. 2 instructions, or 3 instructions because it's saving. So this is what SIMD does. Single instruction, multiple data. Let's take a look quickly at what exists, right? So this is where I actually am talking a little about other platforms. PowerPC has an API. It's called Ultivec. We don't have support for it in Qt at all. MIPS has some support. It's the digital signal processor. They have a couple of others. I haven't seen much use of it. We have some code that does use the DSP. Very limited use. We do have support for Neon in Qt, which is moderate use. You can see the smiley face is pretty happy. It exists a lot in the image manipulation code, where it gains a lot of benefit. There's the old Intel wireless MMX technology for ARM. What the hell was Intel doing with SIMD for ARM? Does anybody remember Strong ARM? That was Intel. Anyway, we don't have it anymore in Qt. We've removed it. The same thing with MMX. We've removed it from Qt. It's completely obsolete. It's replaced by the streaming SIMD extensions, SSC, if you've seen the term, this is what it means, and the advanced vector extensions. Not only do we use it in images like the ARM code, we use it extensively in other places. So where do we use SIMD in Qt? Especially the x86 ones, right? So we use it in Qt core, string handling, like I just showed you. I added a lot of code personally that uses it a lot. We use it in image handling, like I showed. And in Qt 3D, vector and matrix multiplications and manipulation is also using SIMD. The difference that you're seeing there is decision time. Decision time is when do I need to choose that I'm going to use this thing. For the image manipulation, you don't have to make any decision. At runtime, Qt decides for you based on the CPU you have. For the other ones, at compile time, you need to choose that you're going to use this. So as a runtime decision, let's start with the easy one. Runtime decision, you don't have to do anything. Just type configure. It will detect what your compiler supports. So when you see this block here when configure runs, it doesn't mean that you're using this automatically in your code. Don't worry. Don't figure out passing options because I don't want this. This is about Qt figuring out what your compiler can do. And automatically it will use at runtime what it can of these. Today, what we use is basically the first and second line, so SSC through AVX2. AES, I have some code for it, for QHash. I haven't integrated it yet. The SHA extensions would be interesting, but there aren't many CPUs that support it yet. AVX 512, we'll see soon, because currently the only CPUs that support it are servers. That's not very interesting for Qt. But when there are desktop CPUs that support this, would be very interesting. So how does it detect at runtime, right? Where the hell is the rest of my slide? I think this is just a duplicate of the previous one. Sorry. So no, I'm actually missing code here. There was some code. Yeah, the part of my slide went away. Somehow, sorry. Compile time decision. So how do we do it in Qt, right? It's a little more complex, right? The way that it's going to work is that you have to actually tell the compiler, I do want you to use these instructions and don't do runtime detection. Just use them everywhere. You're actually instructing the compiler to generate code using that. And then you're going to get the benefits. How you do this with GCC and Clang, you're going to have to pass extra configure flags to configure or modify your MK spec. Just add, for example, march haswell, which is the equivalent for EVX2. Or you can do for Visual Studio the same thing with -arch colon, not equals, AVX2. I'm talking about AVX2 because that's the most interesting one. For me, at least. You can do it earlier architecture versions, but also because the next slide, which you're going to see. By the way, O3 is not a bad idea at this point. So if you're going to do, tell the compiler to generate code for CPUs that have vector instructions, using O3, which tells the compiler to apply the vectorizer, is a good idea, because then it will look at your code, you're doing this loop, well, I'll just vectorize it for you. It's not always a good idea, not always the compiler does the good implementation of it, but in general, this is a good solution. Qt itself will compile Qt Core and Qt GUI by itself with O3, because it's a very commonly used library. But if you want to pass it for other platforms, other libraries, it's a good idea. There's also a neat trick that I want you to learn about. So what happens if you actually want to do runtime, compile time decision? Let me explain. I want to benefit from AVX2, but I want to be able to run on older CPUs. So what you're going to do is that you're going to build twice. Right? You build once for the baseline for your system, whatever it is, plus once for AVX2, for Haswell. On a Mac, right? You need to export this extra thing here because it will tag the binaries with saying, this is not baseline, this is Haswell. And this is why it has to be this specific. It can't do with other architectures. This is specifically for Haswell. Because what you're gonna see here, let me see if I can show this is easier, right? It has to tag this binary here with an extra flag, which is this age here at the end. This is very specific. You don't have other systems that do it. So just build twice, and then at the end, you stitch the two libraries together with LiPo. On Linux, you again build twice, and just stuck them in a subdirectory called Haswell. That's just it, right? You can do the same thing for plugins. This is a feature that I added to Qt, but that's just it. Just stick them into a subdirectory. That's it. Sorry that I missed one slide.
No worries. Thank you very much, Thiago. Thank you.
Thank you, everybody. And my name is Paolo. I work with eye tracking since 2002. And who has heard of eye tracking before? So there is someone? OK. And who has tried an eye tracker in the last couple of years? OK. So what is eye tracking? Eye tracking is a technology that enables to estimate the gaze position of a person. It's usually performed by a device that is called eye tracker. There are several producers of eye tracker devices. The biggest one is a Swedish company. And it's a 1,000-person company, so it's a big company. And it's not something new. Yes? Oh, OK. It's not something new. The technique is always the same since the 60s. So basically, what has changed was the technology. And what improved? Improved the camera, improved the computing power, improved the electronic parts of the system. There was a breakthrough at the beginning of 2000, and camera was starting to be so cheap and so powerful that was able to be placed remotely. Before, the camera was sticked really near the eye. We're talking about in the 90s or so, VGA camera. And starting from 2002, the first eye trackers with a remote camera started appearing on the market. We are talking about devices that was about 40,000 euros for one device. Nowadays, things are changed pretty dramatically because you can buy an eye tracker on Amazon for $150, and you can plug in Windows 10, and the system just supports it. So things are moving a lot. And so what can you do with an eye tracker, basically, and how it works? It works in a really simple way. So the camera is just taking picture of the eyes, both eyes, because an eye tracker is capable of performing binocular tracking. And basically, it is an infrared camera, so this is a typical image of a device with two active infrared illuminators that you can see in the first image. They are called the glints, so the reflex, basically, of the infrared light into the cornea. Then there is a mathematical model that just tries to find out the center of the pupil, the position of the glints, the position of the head. So there is also an head pose estimation of the head of the person in front of the camera. And the device provides you with the vectors that simply tell the orientation of your gaze. What is the performance of such a system? Commercial devices, like the cheapest one from Tobii, have something around half a degree of accuracy. That it means that they are able, in 1 meter distance, to understand the position of your gaze with an accuracy of half a centimeter. There is a certain a certain glitter on the signal that should be filtered, but the precision and the accuracy is pretty high nowadays. Trackability is amazing because they are able to track around 98 to 97% of the population. It really depends on the producer and the type of a tracker. There are certain trade-offs, but it's a device that is working pretty well with everybody. And use cases. Use cases ranges from automotive, for example. There is someone here in the QtDay that developed an eye tracker for his car. And it is a typical application. Then we have medical system, because in medical there are a lot of situations when the surgeon has the hand busy or you cannot touch. So you use the eye tracker in an active way as an additional input device. And industrial, retails, everything that has Qt inside, basically. So that's why we try to leverage what can be done with Qt, and we try to add another input method to what is already present. So what can you do in a user interface with an eye tracker? Simple example, you can use it as a pointing device for a selection. So you can just look at something on the monitor, on the HMI, on the UID, and with a very high accuracy and a reaction time that we are talking about 700 milliseconds for having the data, you can use it as a pointing device. So you can, for example, point and use a physical button, a single physical button to activate and operate different part of the UI. You can also avoid the physical button if you use timing. So you can tell, for example, if I look at that for half a second, it should happen something. Another example is the scroll of the pan. It's very natural because as the device knows the exact point where you are looking at, it can just adapt the map just to recenter it so that the image provide you with the best viewing angle for what you are targeting. This is actually something that works really, really well and is implemented in several commercial products nowadays. Another example, and the last one right now, is distraction detection. So as we know where the attention of the people is via the device itself, you can just react in different ways with your application. So for example, let's talk about practical use cases. This is not something that has just come out from research. This is actually used and certified in products that are sold, for example, in robotic surgery. So actually in Italy, we have several installations in the hospital of robotic surgery devices that are using an eye tracker as a control and as a safety measure. So they are certified with FDA in the US, and they are certified here in Europe for EU. So I think that once we covered the surgical, robotic surgery as a use case, I think that we can be pretty confident that we can cover also other use cases. What we have done, we tried to let everyone play with this kind of technology. We have seen that you can buy an eye tracker for $100 on Amazon and plug in. Well, we realized a downloadable, a free downloadable actually, plugin for the Qt Designer. So via the Qt Designer in QML, you can define areas that are reactive to the gazes. So you can take a button and you can just tell the button in QML, okay, react to the gazes. If a user is pointing at you for 200 milliseconds, I want you activated. As an example, we have modified the standard coffee machine example without changing anything. In 15 minutes, you can have the coffee machine example working without touching the device, without touching the keyboard. And we are working for having I-controlled kiosk, for example. But the point is, there is a new post in the Qt blob. You can find all the code, references, and download. Everything is in GitHub if you want to try. And included is also a simulator. So if you think that you have a user interface that can have benefit for using the gaze as an input method, you can just try out exactly today.
Thank you very much, Paolo. Thank you. Perfect timing. Yeah. So,
Actually, I don't have one lightning talk. I got 3. So I need to be very quick. Let me start with the first and easy one. The first and easy one is about GammaRay. If you are new to Qt, this is a tool that you definitely want to have inside your toolbox. It's an open source tool that we at QtDay have developed in the last few years. What is GammaRay? It's a high-level debugger and profiler for your Qt application. I gave a talk at this very conference 1 year ago, and people were amazed by it. But I don't have time right now to tell you everything about this tool, so I'm just going to tell you the most important parts. It's a sort of debugger that has Qt knowledge, which means that it allows you to inspect your application from a Qt-specific point of view. How do I get it? Just download it. It's free software. Go there or Google GammaRay Qt. I'm feeling lucky. You will find it. And what can you do with it? You can inspect all the Qt-specific aspects of your application. You can find everything about all the Q objects that are inside your application. You can inspect the Qt widget hierarchies. You can inspect Qt quick scenes, Qt 3D scenes, state machines, and much, much more than that. Just to give you a sample of this, I think I have a small demo somewhere, like right here. Okay. It's a very simple Qt Quick application, just shows a few things. And oh my God, what happened here? Okay. If I run GammaRay and open it against that running demo, which is again here, right? What I see inside GammaRay is the list of, for instance here, I'm seeing all the elements inside my Qt Quick scene. I can inspect one of them if I want to, so I click the inspection tool, say, what is this image right here? And this tells me this is the image, it's got a given anchoring, it's got other properties, and so on. So I can inspect everything, all the state, and figure out exactly what's going wrong in my application. It's a great tool, you should use it. Okay, and that's it. Do I have more slides on this? I don't think so, but so yeah. Second talk, texture compression. Yeah, see, short talks. Lightning talks, that's the spirit. What is texture compression about? Talking about Qt Quick specifically, Qt Quick renders a given scene that you give to it using OpenGL. So let's consider from a very simple point of view what happens when you write something like that inside your Qt Quick scene. You just say image, load a given PNG file, right? What is that supposed to do eventually? That small snippet eventually, under the hood, is supposed to load that PNG file and upload the contents on the GPU in order to be used by OpenGL. Actually, if you go down and see what happens when I write that, a lot of things happen, right? Because the problem is PNG is not a file format that OpenGL understands. So what happens actually when I write something like that is this. The first thing I do is that I read the file from disk, from network, from whatever. The second thing I do is I need to decompress the image. So even if your PNG file is a few hundred kilobytes, OpenGL does not understand that. You need to decompress the image, which means you need to spend CPU time for decompression and also memory, because you need to allocate the uncompressed image. The third step, if your image actually is not in the right format, for instance, it's grayscale, you need to convert it to a format that Qt Quick understands. And at the moment, it only understands RGB32 or alpha RGB32, which then means even more CPU time and more memory being used to do that. Then eventually, you're going to upload this image to OpenGL, and then you're done. And how much does this cost? Well, let's consider that I'm building a fancy application. I'm just considering one particular background for my application. So if I consider a full HD image, that's roughly 2 megapixels. And as I just told you, the only format that QtQuick understands is 4 bytes per pixel, which means 8 megabytes of CPU memory plus 8 megabytes of GPU memory used by one single image inside your application. And maybe you have many of these because you have many screens, and each screen has its own background. And if you're running on a mobile or an embedded device, this just will kill your application. So can we do better? The answer is yes. How do we do better? We are not going to use file formats such as JPEG or PNG. There are specialized formats called compressed texture formats, which are differently compressed, different compression algorithms. The idea of using these algorithms is that they are suitable for direct consumption by the GPU. You can take a file which contains a texture in one of these formats and give it to the GPU as is. Right? So what happens if I tell QtQuick to load a compressed texture format? All I need to do is read the image from disk, upload the image to OpenGL. I don't do anything at all. Actually, I don't even need to read the file. I can just memory map it and then tell OpenGL, please upload that, and done. The image stays compressed on the GPU and gets decoded on the fly only when accessed. Okay? So this gives me a huge benefit in terms of memory consumption. How do I do this practically? Well, I need to compress my texture in a special format, but the good news is QtQuick supports this out of the box. Instead of having your image element point to a PNG file, just make it point to another file format, such as PKM or KTX. Those are standard container formats. And that's pretty much it. If you want, there are also more advanced integration possible if you want to do something fancier. So let me show you that I'm telling the truth, or something that looks like the truth. Where I have creator here, right? So I've got this small thing. I should probably reduce the resolution because this entire monitor is like that. So let me put like, I don't know, 400 by 300. Yep. So I'm running this thing. That's just the image loaded. This is actually a full HD image, so it's quite heavy. And if I find again my shell, which was around here, if I ask how much GPU memory I'm using, that's around 300 megabytes. Don't look at that command line. If there's somebody working at Intel that could please provide me with a profiler for Intel GPUs, I'll be very glad. Okay, so yeah, don't look at that, but look at the number. That's the amount of memory used by that application. So instead, I don't do this. I go here. I change this to PKM, which I have prepared before. I run it again. Looks exactly the same. But now, if I look at how much memory I'm eating, it went down by 2 orders of magnitude, not even 1. Yep. So easy peasy. What is the downside? Well, of course, there is a sad story of this. The sad story is that which compressed textures you can use depends on the hardware that you have. So you need to know in advance, I'm going to run on this specific GPU. That GPU supports just that format, so you need to know that. If you have to build portable software, that's kind of a headache at the moment. The second thing is about the fact that these compression algorithms actually takes hours to run. You need to have this thing as part of your CI. You can't just like, okay, let me compress on the spot, just like as I do for PNG or JPEG. And yeah, that's it. Thank you. Wait. I said, where is it? I said 3 lightning talks, right? So here's the third one, bad programming jokes. Because it's April Fool's Day and I lost a bet, so I must now do this. Please, I did not write these, but try to laugh, making me happy. Okay? So C and C++ walk into a bar, C gets drunk, throws up encapsulation all over the floor, and C++ says, oh my god, dude, have you got any class? Thank you. The 6 stages of debugging. The first one, of course, that cannot happen. That does not happen on my machine. Wait a second, that should not happen. Why does that happen? Oh, I see now. How did that ever work? Okay. C++ 20, I've decided to learn how to use coroutines. Unfortunately, they're actually very hard to use, so I had to give up and yield for the moment. But sometime later, I decided to try again, so I picked them up where I left. Yeah, sorry, this was, okay. Outer genre, you have a problem, you decide to use regular expressions, now you have 2 problems. You have a problem, you decide to use threads. 2 you now problems have, oh, sorry, yeah. What one developer can do in 1 month, 2 developers can do in 2 months. A QA engineer walks into a bar, orders a beer, orders 2 beers, orders 0 beers, orders 1 million beers, orders -1 beers, orders add beers. The bar is put into production. A user walks into the bar, asks where the toilet is, the bar catches fire, killing everyone inside. What happens when you mix a major multinational corporation and your favorite GUI framework? They decide to move to Windows Phone instead and crash into oblivion. What happens when you mix a major multinational corporation and your favorite GUI framework? A popular 90s rock band, and this is very subtle, but sounded cute, yes. Oh my God, yeah. How do you hire good C++ developers? You look at their CV qualifications. Oh, yeah, darker and darker and darker. But last one, C++, the only programming language where your friends can touch your private parts. That's it. No, done.
Thank you very much.
Okay, let's start. So today I'm talking about QML Live-Coding for everyone. I mentioned it previously in my talk. I really like live coding, and now I'm going to show you why it's really cool. So the idea of live coding is actually to automatically reload your QML application. When you modify when you modify your code, pretty simple idea. You work on the code and your GUI just refreshes and reloads all the QML components. With Python, we can extend that to the Python code as well, which is pretty cool. All you need to do is actually you need a file watcher, so something that looks at the file system, and you need to use the QML loader and the QML engine, a few functions from the QML engine, and you're ready to go. And now I'm going to demonstrate why it's so cool. I hope you still can see things. OK, here we go. That's not the correct code here. But instead, we are going to look at this code. So basically, I have integrated live coding in this application. And we are going to run this application now. And what you are going to see is the live coding environment. You will see it starts up showing you all the QML files you have in your project. We are now mostly interested in this page form 1. So we started off in this case with a very simple Qt template. And in this live coding user interface, we can just select this page form UI, and we will see it's just a very simple calculator. And the screen is actually very small, but maybe you can still try to do this. View it side by side. So if you have a big screen, that usually works very well. If you have a small screen, it's a little bit harder to do. And it's not half the screen size. Here we go. So on the left, we have our source code. On the right, we have a QML live coding environment. And when we now edit something in here, let's say, for example, the height of this component, and we save it, we'll see it updates instantly. That's actually pretty useful. We can do, I don't know, everything you can do basically inside QML, it will update instantly. And so that's actually, I find it very useful to work with QML. And the nice thing about this is actually that you can choose all the parts of your user interface. You can also use the main QML file, which is your whole application. You can open your favorite QML editor, which is QtCreator, of course. And you can restart your whole application, which is not so useful in C++, but very useful for Python. And to demonstrate that it also works for Python, I'm going to show you this as well. So this is exactly the same live coding environment, just for Python. For Python, we can actually run it from the command line. So there's a live coding runner. I'm going to start this. This is a very similar application, but in this case, the calculator is actually implemented in Python. Same environment here. But now the nice thing is when we take a look at the Python code, this is the calculator code. It's very simple. 2 inputs, 1 output. It just adds up the values. We just modify this calculate function so it doesn't work anymore. So we multiply our input 2 by 2. Now we can press restart, and you will see our function is updated. So it's very quick and easy to work with when you're working with QtQuick. It's even easier to work with when you're also working with Python. Basically, you shorten the feedback loops. You can instantly see all the user interface updates. And there are 2 ways to use this. Either you're using the run application, like in this case with Python, or you integrate it in your user interface, which is very useful for C++. And if you want to learn more, not going to start again. OK, here we go. So if you want to learn more about live coding on my version of implementation of live coding, visit my blog. My latest article is about live coding and explains it, how it works and how you can use it. And I have 2 projects. One is for C++ and one for Python. Just try it out, use it in your project. In my opinion, that's the quickest way to work with QtQuick, actually. So thank you very much for your attention.
Okay. Thank you very much, Alexander. Thank you. So the next one, the last one, will be Olivier Goffart with the QML Rust bindings. I said before, just 10 minutes for you.
So schon gar keine Cocktails mehr. Okay, ja, dann bis wieder.
So this is not really something I do. But 10 minutes, I'm going to explain a bit what are the bindings for Rust, for QML. So, we all love C++, right? But there are other languages that can do the same. It's called Rust. It's the future. It would be nice if there was a UI in QML for them. Well, wait no more. So this creates, you can find it on GitHub, QMetaObject RS. And you can, so you can write just in Rust and expose your Rust objects in QML. So you just derive from QObject. So this is Rust code. You use the QMetaObject create. You derive from QObject. You have a few properties, some signals, and you can use them. You can instantiate a QML engine, and this works. So let's try maybe to run some example. Cargo run, building, and so this is just a simple example on. So it's a QML UI, but behind the scene we have our model is written in Rust. So yep, it's we expose the QObject of the to-do, and internally we have a Rust vector in our list, but this is a model, and so we re-implemented a few functions which are invocable. They're implemented here. Yeah, it's Rust code. I don't expect you to read. We're between C++ developer. I don't expect you to read all this Rust code, but the point is we created a QObject from Rust. And we implemented the model all with Rust code. Maybe another example, QML extensions plugin. So I'm gonna build, do cargo build. This is gonna build a plugin, and I'm gonna I'm gonna run QML scene with an import path of this directory, which I am, so target debug. So I'm gonna load the plugins that are written in Rust, and I'm gonna run the QML extension plugin example from Qt. Building. Let's hope this works. Some warnings. A clock. But how does, so this clock is, so this is the clock from the examples from Qt. It here instantiates a time object, which the command says it's a C++ plugin, but the truth is I've been porting it to Rust, so the plugin is written entirely in Rust. Our time model, which was written in the original example in C++, here expose properties, the same properties that the C++ code was exporting, but this time with Rust, it just uses a bit of code to get the, yeah, that's a bit complicated, but we also can derive from QML extension plugin. We tell it's a Qt plugin with this interface, and this will just create a plugin for Rust. So how much time do I have left? 3 minutes. Maybe we can see another example. Let's run this example. So this is the graph example from QML, which it's an example that is supposed to show the scene graph. So then again, we have the same QML code as the example from QML. And in that example, the QML file was just loading, was just instantiating this graph, which again is a QObject. It inherits from Qt Quick item, and I'm re-implementing here Qt Quick item for graph, update paint node. So this is really creating nodes of the scene graph, all of that in Rust. And then we run the source just like that. Okay, so I think I'm running out of examples to show. So if there's any question.
Okay, I think we're done. Okay. Thank you very much, Olivier. Thank you.